strings. And so just a few reviews. It's the legendary by Madan Lal Mehta, who was one of the true old-timers. I think he even worked with Wigner and Dyson. And then some reviews from the early 90s. As I will mention in a second, the early 90s was the truly hot period in this field. So 2 reviews by Ginsberg et al. One is by Ginsberg and Moore and Di Francesca, Ginsberg, and Justin from 1993. Then my review, which is more specifically focused on a C=1 matrix model. And then Palczynski's What is String Theory, which talks a lot about that. And then there was another wave of this, speaking now we talk about waves. There was a pronounced wave in 2003, 2004, and 2 very nice reviews by Nakayama and Martinek. And then a very recent, very nice review by Ninas and Millman. Okay, so at first, when I was asked to talk, I got extremely nervous. What am I going to say? And one thing I think about a lot is history. So I thought it would be appropriate to do a bit of history. Of course, it's also the most dangerous subject in the world because, especially talking about history before your time. With profuse apologies, I just want to list a few of the main periods and ideas. So the initial sort of 1950s, 60s appearance of random matrix theory, I think Wigner's idea was that if you take a large nucleus or other complex quantum system, so you don't know the details of the dynamics, but you can think of the Hamiltonian as a matrix sampled from some random distribution, and the most generic one would be the Gaussian distribution. So some of the key advances were made already then, and some of the basic things we hear, the Wigner semicircle law for the eigenvalue distribution, the Dyson guess, and so on. And here there were many key players in that period, and Mehta was one of them, Wigner and Dyson. And then another, I think, key turning point for matrices was the appearance of QCD as a theory of strong interactions. So the key advance then was the gluon field, the fact that the gluon field, which is a Hermitian matrix, sort of entered the scene, and the perturbation theory is in some sense dominated at large N by these loops of the gluon field. And then soon after, in '74, the large N limit, the famous 12th large N limit, entered, and the sorting of diagrams according to their genus and the dominance of planar diagrams. And already then, I think the idea of Feynman diagram as discretized random surface kind of appeared. Then I think a very important paper was in 1978 by Brezin, Parisi, Itzikson, and Zuber, solution of the large N non-Gaussian matrix models and the technique of introducing the integral equation for the eigenvalue density. And that paved the way for a lot of formal advances a few years later. Okay, so then the stringy approach, the sum over continuous surfaces, non-critical string theory and superstring, was of course in the famous Polyakov paper from 1981, although maybe he wrote it much earlier. In those days in Soviet Union, there was censorship, so there were delays, but I'll just list the date of the paper. And the appearance of Liouville theory coming from the two-dimensional geometry basically was around then. And then around starting between 84 and 88, there were actually already in the early 80s, there were some ideas about discretized version of string theory, the kind of mechanistic approach to either the Nambu-Goto string or the Polyakov string. And one prominent model was the Weinstein model, the model of complex matrices. And then some development later led to basically development of this idea of matrix models giving discretized random surfaces via Feynman graphs. There was a very nice paper by Kazakov and then follow up by Kazakov, Kostov, Migdal, and the independent work by David and Ambjorn Durhus Frolich. So for the basic pure geometry that already appeared in '85. And a few years later, Kazakov and Migdal introduced the C=1 connection. So just everyone knows this, but the basic story of integral over a matrix generating random triangulations is in this picture here. Okay, these are the double-lined Hooft graphs for index flows, and their dual graphs are just random triangulations. Now, the story of connection between this and continuum geometry, it's a kind of heuristic in this field. We just say that we can replace some of our geometries by this sort of Reggie calculus, where all the curvature is in these places where triangles meet. So just heuristically, you say that these two different formulations should give the sum over random two-dimensional geometries. This is still, I think, an unproven connection, but it works in all cases that we know. Okay, so now the development on the string theory side, late 80s, is the first precise connections between matrix models and Liouville theory. The so-called KPZ-DDK scaling, Knyzhnik, Polyakov, Zamolodchikov, who were working in two-dimensional light cone gauge, and then David, Dissler, and Kawai, who basically invented the Liouville approach to the problem, which turned out to be extremely fruitful. And there were agreements between the scalings, for example, of the path integral as a function of area between the two approaches. Then I think a key year was 1989, where the double scaling limit was realized. This limit involved scaling so if you look at this coupling constant G, to make, you have to scale this G to some critical value to essentially enhance the contribution of large Feynman graphs. And then if you simultaneously scale it in a certain way and take n to infinity, you can also enhance higher genus surfaces. And this was realized in these papers here for the C less than 1, and also these papers, Gross and Milkovich, present Kazakov, Zamolodchikov for C=1, the matrix quantum mechanics. I should say that the leading solution was already obtained in this famous PIPZ paper in 1978 for both types of models, but then it was realized that you can enhance higher genus. And there was actually a lot of excitement in 1989 about this. And 1989 to 94 was the period of flourishing of the field. I was thinking of a silly term for that period. Maybe it should be mania or something like that, for matrix model mania. And it was a pretty abrupt transition, which started late in '89. And then lots of young people joined the field. As a full disclosure, I was one of those young people. And I remember if in 1990 you walked up and down the theory floor in Jadwin Hall, basically everyone was working on matrix models or Liouville theory one way or another. And definitely a lot of good stuff was done then. There were various further precise comparisons between matrix models and Liouville theory. Now, Liouville theory was a difficult beast, considered a very difficult beast because of this complicated measure, as emphasized already by Polyakov originally. And even after DDK, it was not totally clear what to do. but some special correlators could be done using a free field technique. And one of these correlators was the torus free energy, just the genus one path integral. And Bershadsky and I computed in 1990 for t less than 1 and c equal 1, just did an exact calculation. Much more difficult were correlation functions, and there was the Goulian-Lie trick of resonant correlators, which was similar to this. And then DeFrancesca and Kutasov applied it to some amplitudes. And I think one of the very big things in that period was the physical picture for the C equal 1 matrix models as two-dimensional string theory, because this collective field theory approach for ripples on the Fermi surface by Dasenjevitsky and others basically allowed us to think physically. So the C equal 1, it has a continuous dimension. So you had something like dress tachyon operators, but an added advantage was that these tachyons were not really tachyons. They were just massless modes of the string. So it added up to a very beautiful theory. Now, from the point of view of the matrix model, there is a free fermion approach. So if you write this, this type of matrix quantum mechanics with an unstable cubic potential and take the formal large N limit, then you get a set of free fermions, and you fill the Fermi surface up to some level very near the top of the potential. Then in the double scaling limit, you just get the upside down harmonic oscillator filled to some vicinity of the top completely. And then you can study ripples on this Fermi surface. So the signals would propagate from far away to this turnaround point and back. And this was interpreted as a kind of boundary S matrix. And these calculations were done. In particular, a very efficient technique is Moore-Plesser and Ramgoolam. And various other ways of bosonizing these non-relativistic fermions were in these papers. So this was a really interesting progress. And the question was, what does it have to do with the continuum non-critical string? There were definitely some checks that it does have to do with it. For example, one thing is that the free fermions had some infinite symmetry, and the discrete states of the C equal 1 string theory did implement W infinity symmetry. There was also the ground ring approach invented by Witten. And one very interesting thing, consistency check, was that if you look at the singlet sector of the matrix model, then you actually do get T-duality, the R-to-1 over R duality for compact C equal 1, which is really matrix model at finite temperature. So this was a check that really this approach, even though initially people were not convinced, these calculations, I think, convinced people that this really does correspond to continuum non-critical string theory. Then there was lots of other really great stuff for mathematics, a Penner model, then developed by Distler-Waffa, the Kontsevich model for moduli spaces, topological string theory. And then somehow around 94, this party kind of ended rather abruptly. I don't know, maybe people felt like, it's been a while, but I think the dominant thing was this dramatic progress in supersymmetric gauge theory, and in particular the Seiberg-Witten papers. So the same young people who came running in 1990 basically came running out this door in 94. I was, as always, a bit slow to come in and to leave. But the amazing thing was right around when everyone left, the real breakthrough happened, which was this DOZZ solution of Liouville theory, which in some sense developed this Goulian-Lie approach, but much more powerfully. So there were this Dorn-Otta and Zamolodchikov brothers papers. So yeah, the picture I have now, you see these movies about hurricane on some islands, and then there is a 2-lane highway. There are like one way it's completely clogged by the cars, and the other way there will be like 2 or 3 cars. So these were the 2 or 3 cars that were coming in. And in retrospect, they turned out to be fine. But definitely the rate of the number of papers dropped off very sharply around 94. And of course, in 95, 98, there was a great period of string dualities, D-branes, ADS, CFT. And at that time, it didn't seem so connected with this matrix model non-critical string story. Although I think some of us were very motivated by the C=1 story. It seemed just intuitively similar to ADS-CFT duality. And I think what was waiting to happen is to kind of make this connection better. Then again, largely through the efforts of the Molochikov brothers and collaborators, people understood. So we know that the way we think about ADS-CFT is we think about stacking D branes, right? So we stack these 3 branes, we get n equal 4 super n mils, and then there is a dual closed string description. So something like this started appearing around 2000 with the discovery of smeared and localized D-branes in Liouville theory, in particular the localized D-branes. And these are the ZZ branes. The smeared ones are FZZT branes. And actually, Polyakov has some notes. He noticed these ZZ D-branes, and he had this prophetic paragraph in his 2001 notes, which essentially said something about, so these ZZ D-branes are localized at large value of Liouville field, and whether they have something to do with matrix models, like stacking these ZZ branes have something to do with matrix models. And then in 2003, 2004, there was actually another big wave of activity along these lines, and the answer is basically yes. And it brought this matrix model non-critical string duality, I think, a lot closer to the gauge string duality. In particular, it was realized that the C=1 matrix model can be thought of as effective theory on n unstable ZZ D0 branes. Right, so there was McGreevy and Herman Verlinde paper, and then my paper with Maldacena and Zyberg, which in particular stressed these localized D-branes. And another really nice thing from that era was the new hat, namely, basically it was realized that even models with fermions on the world sheet somehow can be incorporated in essentially the same type of matrix models, except they have some additional Z2 symmetry. And this was in these papers. This picture actually is not from 2003, it's from my review in 91. And in fact, people were already then wondering what happens if you fill both sides of the potential. Does this give you just some non-perturbative regularization of the same string theory, which prevents the fermions from tunneling out, or is it something else? And I think this really was answered in 2003. We realized that this actually gives, in some sense, a nicer non-critical string theory, the type 0 theory. It's still tachyonic. You still have unstable D-branes signified by this upside down harmonic oscillator. But it does buy you some improvements in the behavior of the theory. Okay, so now, so then I think, I hate to say this, but I haven't really kept very close track of the field since then. It has been making progress, and for example, a more precise matching of correlation numbers in multi-critical matrix models were accomplished by Belov and Zamolodchikov, and then basically further progress was made. It's a very subtle comparison, but it finally appears that it works. Now, something a little bit different, maybe closer to the original Wigner random matrix theory, is the large N SYK model, which is solvable via summation of Melonic graphs. And that is a kind of random Hamiltonian that can be approximated by a certain random matrix, which is a very hot topic right now. But so it feels like, so I think there have been already two huge waves, or two big waves, one in 89 to 94, and the other one a bit smaller, now 304. It seems like a new wave is building. There is this Jackiw-Teitelbaum gravity, and also supergravity can be described by certain large N matrix models. First, this was found in the Schenker-Stanford paper. And interestingly, they may be described by limits of matrix models studied much earlier, including the unitary and complex matrices, as a nice recent work by Clifford Johnson. And then another important development is non-perturbative completion of the C=1 matrix model, including the tunneling of these branes. This is just filling one side so far. So this is really something that we were always scared about, which is this problem, because eigenvalues can really tunnel out, but it looks like it's possible to make sense of that. And we'll hear much more about this. And these ZZ localized instanton calculations also can be matched with string field theory calculations by Ashok-Sen. Okay, so now I just want to say a few things that I think everybody knows, but I don't want it to be a pure history talk. So just bring up a few things that came to my mind as I was trying to prepare this. So non-critical string theory, well, we all know what this is. This is just sum over topologies, and then you sum over the metrics and the embedding coordinates. So this is what we call Polyakov string theory. And now originally this action just includes the dx term and the worldsheet cosmological constant. So it's really two-dimensional quantum gravity coupled to C massless scalar fields. So this particularly simple example is C=0, which is pure quantum gravity, and C=1, which is that coupled to a single scalar field. So now in the continuum approach, you adopt the conformal gauge, and then there is induced dynamics for this phi field. And finally, in the DDK approach, you get this theory with the linear dilaton, right? You have this, it acts like a scalar field, but there is no translation invariance in the phi direction. There is this Frodkin-Saitlin Q R hat phi coupling, and there is the exponential Liouville wall, so to speak. So this establishes that the non-critical string in C dimensions is like critical in C+1, but there is no full Poincare invariance, of course. So now, so the basic formula from the early days, from the late 80s, is that this Q is square root of 25 minus C. And then when you dress the identity operator, there are two solutions, right? Alpha plus and minus. And you immediately see that something funny happens when C is bigger than 1, right? Because then the two solutions become complex conjugates of each other. And then this becomes sort of a complex term. It no longer, it's also oscillating rapidly. So one of the steps in those days was the Seiberg bound. Basically, Seiberg showed that you really have to take this operator to be non-normalizable in the Liouville direction, and this selects alpha plus as the bigger one, the faster growing one at large phi. And this was actually what matched all the scalings of the basic matrix model. So if you look at the partition function at the fixed area, through this DDK technique, people obtain the gamma string as just 2 plus q over alpha plus. And this magically agreed with the solutions of single trace matrix models. And this gave people faith that something interesting is happening. And in these single trace matrix models, the susceptibility exponent gamma string was always found to be negative. While earlier in the mid-80s, people were very unhappy about the phases of the theory where gamma string is 1/2, which is this branched polymer phase. That's not a stringy phase, and that's what we're always kind of afraid of, that the models will lead to this phase. But now, so people, one thing that you don't hear much about now, but was very much part of the language, was the C=1 barrier. Dressing becoming complex for C greater than 1. And this really is related to the fact that the theory becomes truly tachyonic for C bigger than 1. Namely, if you compute appropriately the mass of the center, mass squared of the center of mass degree of freedom, it's 1 minus C. So at C = 0, we're just spared, but C bigger than 0 is no good. But people were very much obsessing about solving this penetrating above C = 1 barrier, because that's, of course, where we want to be if we want to study random surfaces embedded in more physical dimensions. And so there were corresponding problems observed in discretized formulations, for example, in Weingarten models and then Eguchi-Kawai. There was a paper by Durhus, Froelich, and Jonsson who basically proved that certain models were in the branched polymer phase. I think now maybe we don't hear much about it because ADS-CFT has in some sense allowed us to reach above the barrier. Because there you don't have the linear dilaton non-critical string, but you just have another background, ADS cross sphere or ADS cross Einstein space. But I'll say a bit more about this in a second. So just one thing that in desperation about C = 1 barrier, so one thing that at least I was trying to do around 92 was just something brute force. Like suppose you just write the matrix theory not in 1 dimension, but in 2 dimensions. That, of course, is no longer solvable. You cannot reduce it to eigenvalues. It's just it's not clear this makes sense at all. But we tried to apply light cone quantization to this theory and sort of wrote down light cone wave functions. And one thing that you would be looking for is if there is a Liouville field, the spectrum of mass squared would somehow become continuous. And this is a paper no one knows about. It's sort of, I would call it a very feeble attempt to go above C = 1 barrier. But it sort of points to some of the difficulties. Even if there is some Liouville sign of Liouville field and continuous spectrum, there will still be a tachyon. And there is another very big problem about these type of theories, that these string-like wave functions, which are single trace, there's nothing that prevents them from falling apart into string bits. In other words, the non-singlet states are perfectly okay and have finite energy. No one told you that you have to have just, states with no indices. And this certainly, so the problem is that there is really no confinement in pure matrix models which are not gauged. And strings can fall apart into bits. And this, in a sense, can be cured by gauging the SUN symmetry, but that, of course, makes the theory even more complicated. But it sort of points to the fact that you should probably be gauging, especially if you go above the 1 dimension. Now, another interesting question, which I have from the old days, is about double trace matrix models. So if you, for example, take the single trace matrix model and then just add trace phi to the 4 squared, then it adds some kind of touching interactions, which are like world sheet Euclidean wormholes. And at leading order, you get trees of spheres. So you find trees of touching spheres. Now, this was originally studied by Dast, Harrison, Gupta, and Vadia, and gave very interesting results. So for small double trace coupling, the model was in the same universality class as single trace. For large G, it was just dominated by this term and was in the branched polymer phase, gamma equal 1/2, which just signaled that it's really dominated by particle dynamics. But there was a special value, special tuned value of G, where the string susceptibility jumped. And there seemed to be some new universality class. People were even wondering if this was a way to get above C equal 1 barrier. Because so essentially, for example, for pure gravity, you instead of -1/2, you get susceptibility plus 1/3, which is not smaller than 1/2, but something puzzling. And I actually realized in '94 that there is a way to phenomenologically explain all these new susceptibilities by replacing alpha plus by alpha minus. Then it explains all these jumps that happen in matrix models. And because the new susceptibility is related to the old one by this very simple formula. And in particular, the double trace model can be solved non-perturbatively also using Hubbard-Stratonovich trick. And at leading order, you just get the Legendre transform of the single trace partition function. Now, this was done like right around the time when everyone lost interest in this. So I'm still not sure what is the precise meaning of all this in terms of the modern understanding of Liouville and the DOSZ formula. I think it would be interesting to sort it out because maybe it's in disguise just the same Liouville theory that you get before the transform, but it's not obvious. And it certainly does appear like seemingly a new type of matrix model. Now, another general question is reduction to eigenvalues. So the secret of solvability of these simple matrix models is the reduction from n squared to matrix degrees of freedom to n eigenvalues. But in a typical matrix field theory in D greater than 1, this reduction clearly does not happen. They're not exactly solvable. So the maximal matrix model where such a reduction happens is matrix quantum mechanics at 0 temperature. Once you go to non-zero temperature, this compact C equal 1, you have to, in principle, include the non-singlet sectors. And we understood with David Gross back in 1990 that they really correspond to worldsheet vortices, which are created by the winding vertex operators. So they're actually dynamically suppressed at low enough temperature, but above the BKT phase transition, they get liberated. So the non-singlet sectors in matrix quantum mechanics kind of correspond to winding states, and they're really part of the string theory. Their understanding was greatly advanced in the Lorentzian continuation by Juan's paper in particular in 2005. They're related to semi-infinite folded strings that can kind of move dynamically. They don't sit still, they just come in and go out. And the fact that they're semi-infinite explains why they cost so much energy in the scaling limit. So this is related to another dream from the old days, which is understanding black hole dynamics. So this two-dimensional string theory contains black holes, as was emphasized in these papers already in 1991. Now, one of the big pushes was to connect these black holes with C equal 1 matrix model. Now, since now we know that black holes must exhibit quantum chaos, the integrable singlet sector of matrix quantum mechanics, the free fermions, just does not provide enough degrees of freedom to account for black hole chaos. But the non-singlet sectors are really there, and they're much more complicated, and they appear to provide what the needed ingredients are. So in the Euclidean black hole, the Kazakov-Kostov-Kutasov paper was very nice, which built on the earlier work of Bulatov-Kazakov on the upside down harmonic oscillator and non-singlets there. And then in the Lorentzian dynamics, this folded string story comes in handy, but I think more needs to be done to fully understand this sort of dynamics of black holes in real time. And now we know that there has been great progress on black holes in JT gravity. In this case, I think we have the added advantage that the theory is really embedded in string theory. So we have even control over higher genus correction, and everything is very constrained. Now, another sort of getting a bit more closer to physics is the confining strings. So this certainly has been one of the driving forces for studying large N, because expressing confining strings using dual flux two variables has been a dream for years, and many people contributed to it. In particular, Sasha pushed it for many years. And now from the ADS-CFT, we learned that even some conformal field theories have, like N equal 4 superrank mills, have strings in them. They're just type 2B strings in this curved ADS background. But then we can further deform them to have confining examples of gauge gravity duality, like N equal 1 via the conifold type constructions. But these are, they don't yet teach us something about truly confining strings in asymptotically free theories. They're in sort of these cascading theories, which are a bit more unusual. So I think confining strings is very much a part of non-critical string theory, and they are something that even is connected to lattice gauge data and so on. So in these warped throat backgrounds, confining strings are just fundamental strings that sit at the bottom of the throat. And this suggests that they have additional massive degrees of freedom corresponding to basically fighting the subtraction from the warp factor. Another approach is just take lattice gauge theory and study it at large N. And a lot has been going on more recently in this direction. They also suggest new degrees of freedom on the string world sheet, in particular world sheet axion. And more from the bottom up perspective, you can just study string effective actions and look at extra terms compared to non-Bogota action. And this can be compared with lattice simulations. So for example, Polchinski-Strominger work, and then more recently, Aronik and Margotsky were trying to classify the higher dimension operators and compare them with these terms. There's clearly life in this field because numerical work is getting more and more precise, and we're bound to learn more from this direction. Now, just to finish the talk, many remaining questions. I mean, as I said, I'll be followed by Shi-Yin, who has been working much more recently on this. So my questions are partly come from the distant past, but some of these problems really still haven't been solved. I think on the big picture level, can we prove the matrix model non-critical string correspondence? I think we have two perspectives on it. One is this original via discretized world sheet and planar Feynman diagrams. Then there is the D-brain perspective from 2003, 2004. But this is certainly should be simpler than proving ADS-CFT, but there's still no proof. Then on a more specialized level, what about multi-trace interactions? What is their precise connection with Liouville? Now there is the new matrix models for JT gravity, which are much sort of closer in spirit, the philosophy to the original Wigner idea of random matrices as random Hamiltonians. But they appear to be connected nevertheless to the Liouville theory models that were studied earlier. Now, in spite of many solutions of matrix models, there are still this is just the tip of the iceberg that we understand. And would be great to develop at least approximate techniques to solve matrix models that cannot reduce to eigenvalues. And there was recent work by Henry Lin and Han Hartnell-Puthoff. Now, a specific model that seems to keep cropping up is this C=1 matrix model, in particular the compact version, because it looks like just on the boundary of solvability. Even though there are non-singlet sectors, they are more under control. But still, some very basic things have not been computed. For example, correlation functions for mixed momentum and winding operators. This should definitely be doable, but I don't think there are formula for that. Of course, the hope is that this will also bring in better understanding of 2D black holes. Now, one thing that's been going on recently is large N tensor models also, which are SYK-like. The question is, can this teach us something different about quantum gravity? And let me just end with large N gauge theory. I think this has been sort of a big driving force. We know that confinement creates string-like bound states, but we don't fully understand the sort of world sheet description of this theory. This clearly makes sense above the C=1 barrier or 1D barrier. In some cases, there are other techniques for solving them. For example, the 't Hooft model, also two-dimensional models with a joint matter. They're not solvable, but at least some special points of them seem to be under good control. So one dream is a description of confining strings or superstrings. And maybe one example that might be under better control than the standard non-supersymmetric pure glue theory would be N=1 supersymmetric theory. In that case, there is certainly no stability problems due to tachyons, and maybe more contact can be made with lattice gauge theory there. And finally, this is a bit brave, but I think it's a perennial question. What exact statements can we actually make about, say, large NQCD in 3+1 dimensions? And the dream, at least I think a dream should be, can any of this, say random surfaces or other matrix models, can we make some contact with experiments of any kind? It doesn't have to be accelerator experiments, could be some lab experiments. So, thank you.
So I think we should all thank Igor for this very nice and inspiring review. And we have time for questions and some comments, if somebody wants. You can just unmute your microphone and directly.
So I have a question. Igor, in the one of your last slides, you asked for a question: can we prove the connection between the matrix model and the C=1 world sheet theory? What more do you want? I guess is the question. I mean, in the early days, there were these, checks of S matrices and so on. And then in the 2003-4 period, we figured out what the relation was between the eigenvalues of the matrix model and D-branes on the world sheet. So what more are you looking for?
Well, I think the idea of the correspondence between a stack of D-branes and the closed string. So it's an example of open string duality. Fine, maybe it's a physicist's proof, but I think it's still somewhat heuristic, right? Why? So we usually say, for example, we don't consider this a proof of ADS-CFT, right? Like when we stack ND3 branes and then we get unequal force superagnose, and we get the curved background. And I consider this a very strong suggestive argument, but I'm not sure people would broadly consider it a proof. I mean, I think the one thing that definitely, I mean, I love this period in 0304 because it departed from just the idea of discretization of the world sheet and made it closer to how we think about open-closed dualities. But, you know, maybe it's almost there, but.
Can I make a comment on that about this the ZZ brain story? To me, it's on much weaker footing compared to the decoupling limit that leads to ADS-CFT, and I wouldn't consider that to be a proof, just because you know, this tachyons, open string tachyons, the ZZ brain, it's true that they agree with this fermion Hamiltonian near the tip of the potential, near the top of the potential. But once you go, but that's not enough, right? Because we're trying to describe a situation where the open string tachyon have condensed, and just to see that they agree at the top of the potential, that's not enough. In fact, we know that if you actually study the open string tachyon dynamics, as Ashok famously conjecture was proven by Martin Schnabel, it's exactly the same story in this as in critical bosonic string theory, that the tachyon potential drops down on one side, on the left side, the wrong side, but it kind of, it flattens out on the right side. Right? So that's the theory you would have, you should be seeing from the open string tachyon dynamics. And what it captures is not the fermion in the matrix model Hamiltonian, but the fermion, supposedly the fermion in the presence of the Fermi state. So that is not at all obvious if you just know the dynamics. This is to say the spectrum of tachyon. So I think that's very far from capturing full dynamics. I mean, for example, what I would love, and I thought I'll mention this myself, I would love to see actual justification, you know, derivation, say, based on open string field theory that demonstrates that the effective tachyon dynamics is actually equivalent to the fermion in the presence of the rest of the Fermi surface, Fermi state.
I guess another thing I should have said, yeah, thank you very much. I mean, I don't have insight into all this recent progress, but yeah, I'm sure we'll hear more from you about it. But also, like in this case, the stack of ZZ brains is of course unstable, right? While in ADS-CFT, it's perfectly stable because of supersymmetry. So I think
but in the 2003-2004 period, the instability was just interpreted as the classical trajectory of the eigenvalue. So yes, there's an open string tachyon, but the tachyon condensate just describes the classical motion of an eigenvalue in the inverted harmonic oscillator.
Right.
Yeah, I mean, the instability is of course expected. The thing that I don't feel satisfactory about that is just knowing that instability is not quite enough. You want to know what happens when the open string tachyon develops a large value.
Well, I mean, this is why we're here. I mean, this is
right. Yeah, that's a question, I guess, of computing the closed string interactions with that in the presence of that condensate on the D brain, right? So if you want to ask, well, how does that particular eigenvalue interact with the rest of the Fermi sea? That's a question of computing open-closed correlators on that D brain in the presence of the tachyon condensate. And that has indeed not been done, as far as I know.
So I have a question on multi-trace deformations. So you explained that they correspond, in terms of the worldsheet, they correspond to wormholes, or you can interpret it as changing the Liouville dressing. But is there any understanding what it means from the target space point of view? when you consider multi-trace deformations? For example, if you consider, I don't know, some collective field theory description of these models. What does it
I
mean?
feel like, yeah, this has not been fully clarified. I mean, these papers we wrote were just around the time when people left, as I said. So, and I think that as full disclosure, some people certainly don't find it satisfactory, this story with dressing of, change of dressing. Because I think what DOZZ taught us is that there is only one Liouville theory, which has this B to 1 over B duality. So that's why I'm asking. I meant, actually, I remember one historical note when the late Steve Gubser came back to Princeton and in 95, like late August 95. And we worked on matrix models before then. And I told him, let's read the DOZZ paper and try to figure out what these matrix models, double trace matrix models, have to do with this DOZZ. But then 2 weeks later, there was Joe Polchinski's D-brain paper. And of course, we dropped it. And so this still is not clear to me. But there is definitely phenomenologically it works. So that's one thing. So what my worry is that this phenomenology is a little bit misleading, and then when you focus on somehow invariant quantities, it's really the same theory. But this needs to be straightened out. And yeah, I don't understand what the change to space-time picture is because of this.
Right, because I would expect, for example, that it introduced something like correlations in the collective density of the fermions.
Right.
So
yeah, another thing is that when the coupling is weak, as I mentioned, when this G is weak, this interaction is really invariant in the double, irrelevant in the double scale. So you really need to sort of crank it up to just this special non-perturbative fixed point, which luckily is solvable because we know how to solve double traces via this upward Stratonowicz trick. But yeah, it's all quite mysterious. At the same time, like people worked a lot on double trace operators then in ADS-CFT, and there is a whole never-ending story about that. So it would be nice to understand it.
Yeah, I just wanted to ask about that point. So does the ADS-CFT insight tell us something? Because in the case of ADS-CFT, the worldsheet theory becomes non-local.
I'm not sure that's widely accepted. This
point. Okay. Well, but the target.
I remember when we were discussing double traces.
Right.
I mean, there is just this insight that in the semi-classical limit, it just changes boundary conditions.
Well, but that's the target space, right? And and I thought like the worldsheet interpretation is that it becomes non-local precisely because of the wormholes.
Okay. But yeah, but this most people have only used this boundary.
Well, in practice, it's not useful for the computation. I agree.
Yeah, so you could say, but yeah, you could say that the worldsheet theory becomes non-local, and I thought that somehow rang the bell with this, the fact that this other operator, the fact that it's normalizable, it's a kind of, becomes a sort of non-local thing, right? Like you usually want non-normalizable operators because they are the local ones. They're the ones that are dominated by large phi, but this is not true of this alpha minus dressing. So if someone can help a little bit, that would be nice.
So actually, I had a quick question. So you mentioned that at some point the C=1 case became to some extent similar with the standard ADS-CFT picture. What about the C<1 case? Should we put those in a logically distinct footing, or?
No, I think, for example, so this is what Clifford Johnson will probably talk about. I mean, even for pure supergravity, there are similar ideas there. There are these double cut matrix models. So for example, if you look at what happened for C equal 1, right, the main thing is that the worldsheet superstring, even though it doesn't have space-time supersymmetry, the eigenvalue has this two-cut structure. Now the unitary matrix models, or some Hermitian ones, even for C equals 0, has this two-cut structure. And so we wrote a paper with Senna and Zyberg in 2003, talking about C hat equals 0 theories of that kind. And we're building correspondence again with type 0 theory. So I think the logic extends to C less than 1 models, but maybe it certainly hasn't been explored as fully yet.
Well, there were these very nice papers of Zyberg and Shi.
Right.
Basically used the same sort of technology that was used for the C equals 1 model to describe the C less than 1 models.
Right. Yeah, thanks for bringing it up. Yeah, that I think is a state of the art for
Well, I guess what I find more puzzling in the C less than 1 case is how we make sense of the Hilbert space of the theory, because it's no longer a quantum mechanics.
Right, but you can still talk about the what are the set of operators, what are the set of correlators, right? I mean, they're no longer correlation functions, but there are some integrated correlation numbers that people compute.
Yeah, I think you should think of it as a theory in sort of a discrete Euclidean time that's a finite interval. If you want a space-time interpretation, right? I mean, the microscopic models were, the unitary matter theories could be described as the target space is like a Dinkin diagram, and the lattice. So there are at least, in the universality class of these models are models where you have a random surface, and the matter model is some lattice theory where the, some kind of discrete spin model where the spins can take some discrete number of values. So, I mean, if you want to think of that as some kind of discretized target space, where you have a Euclidean time is a finite interval. I mean, that sort of description is available, but I'm not sure it's particularly useful. I mean, the concrete things you calculate, as Igor said, are some list of correlation numbers.
Yeah, I should say that in this paper we wrote in 2003, which is right around the time I semi-decoupled, we did look at multi-critical models. And I mean, similar to Kazakov's original multi-critical matrix models, they do correspond to non-unitary, basically non-unitary models with C hat negative coupled to worldsheet supergravity. I think we built a pretty strong case, and then indeed Zyberg, Maldacena, and Shi developed it further. So I think the philosophy there is very similar to what was going on in the late 80s.
So Sumit and Antal, I think they raised their hand, but I was a bit slow. So if you want to still speak.
Can I ask a question?
Well, actually, my comment was just about this question of double trace deformations, which you mentioned. With ADS-CFT, you also have this Legendre transform. So, I mean, it's something very similar going on there.
Yeah, I mean, actually, there was some causal connection there because I knew about Legendre transform, and then when we were working with Witten, I just said, well, it should be something similar.
Yeah. But
in that case, it's very clear it happens because of these modified boundary conditions and so on.
Right.
So in that case, we understand that it's some duality between actual sources and expectation values. maybe something similar is going on with this Liouville theory, but I don't know if it certainly hasn't been worked out to people's satisfaction.
Okay, so Gifan? Sorry.
May I ask you?
So I have a question related to, may I proceed?
Sumit was continuing, or yeah, I lost the. So Gifan, yes, continue.
Oh, no, I'm done. Okay.
Oh, okay. Yeah, so I have a question about the relation between the more conventional ADS-CFT dualities and this matrix model type dualities.
Mm-hmm.
So is it possible in principle to embed this kind of matrix model duality within a more conventional ADS-CFT duality, like the ones involving ABGM or exposure binomials?
I think the thought
maybe by partly doing some supersymmetric twist on some transverse directions.
Yeah, I'm not sure I know the answer. I mean, one thing that I think has not been fully accomplished is anything with space-time supersymmetry in these like C hat less than or equal to 1 models.
Right.
But there is definitely the story with linear dilaton holography for NS5 brains, which is somewhat reminiscent of this. So people worked on that already in the, sort of from a gauge gravity point of view.
Right.
That is somewhat similar to the linear dilaton holography you see here. In particular, you don't have ADS boundary conditions. You just have something like little string theory, right?
Right.
Yeah.
Yeah,
so
that's linked to poor Liouville case. Right?
Yeah. So the little string stories. I mean, I didn't mention little. I probably should have mentioned it, but I had a finite amount of time. Another thing I didn't mention is these matrix models for ABGM type theories on the sphere, which also was a very big phase in matrix model technology. But I mean, matrix model is a semi-infinite field, so.
Right. Yeah, the reason I brought up this question is related to what Shota was asking, is because this double trace deformation that you mentioned has a very natural interpretation in the context of conventional ADS-CFT as changing the boundary condition. So if we were to able to, embed this kind of matrix model duality within the, say, ABGM theory, that may give a way to understand the meaning of this deformation on the string worksheet.
Okay.
I ask a question here. Hello?
So Volodya has a question.
Yeah, it's about the C=1 in compactified time, which is, as we know, the model of two-dimensional gravity interacting with vortices, with one-dimensional compactified field. And it's Berezhinsky-Kosterlitz-Taulis model coupled to gravity. Then we managed to identify the corresponding matrix model, which describes this with the black hole, with Kutasov, Kostov, only for one radius of compactification.
Right.
There it corresponds to Vezzo-Mina-Witten black hole. But what do you think about other? I mean, there is the whole line of dense vortex phase, which probably has black hole-like behavior. Do you have an idea how to describe it on the Liouville side or by other methods? Or
well, it could be some kind of singular background, like where instead of smooth cigar you get something singular. That's one.
But from the point of view of statistical mechanics, this phase behaves very nicely.
Yeah.
So
can I comment on that? I think one should distinguish the C=1 vacuum at finite temperature from the black hole. These are two different backgrounds. So if you just talk about C=1 vacuum at finite temperature, one can actually make sense of observables like S matrices. In fact, the formula for this has already been computed by Igor like many years ago, and they're meaningful because the background is such that the coupling dies off at infinity. So asymptotic states are they're free in asymptotic region. You can talk about the finite temperature version of scattering amplitudes, and this formula makes perfect sense. I think the black hole is a different background that can be sort of deformed from the worksheet point of view, deformed away from this vacuum.
But
Yeah,
Sine-Liouville theory seems to be perfectly dual to this black hole, yes?
I will have some, actually, both me and I think Bruno on Wednesday will have some more precise comments to say about this deformation.
Mm-hmm. Maybe.
Yeah, I think the third day of the workshop
will discuss it.
Specifically for that.
Mm-hmm. Yeah, but it's probably misleading to characterize the background, the Sine-Liouville background as a black hole, because I mean the Sine-Liouville and the cigar are strong weak coupling duals of one another, and the regime that is described by the C equals 1 theory is where the Sine-Liouville coupling is the more weakly coupled one. So we never use the more strongly coupled version as the good effective description of the dynamics. So thinking about the background as being a Euclidean black hole is probably a mischaracterization of the proper effective description.
But Emil, can I ask something?
Actually, I disagree with that. I think it depends on the temperature. But anyway, I mean, probably it's not a time to get into this. But
it may be.
Maybe this is a discussion to be had on Wednesday.
Yeah, we want she to have some time to talk.
Yeah, let's see.
Yeah, black hole is sort of one thing where there's been a lot of progress, and at the same time, as you can hear, there are many questions still. And I mean, if we can really nail the black hole, that would be like a big success of this approach, and really compute something that we know black hole must do, right? So.
I have also another question about the sequal zone barrier. So are there any other models in which you can go beyond the sequal zone? For example, in BFSS, you definitely go beyond that, right? So you could imagine introducing, I don't know, multi-matrix models, more than one matrices that depend on time, let's say, that are interacting. And then you can go beyond that, right? That's another way of...
Right. So in supersymmetric gauge gravity duality, but then, yeah, the whole point was, this is actually something Polyakov in a sense suggested early on, that instead of taking just the metric, the worldsheet theory of the type dx squared plus d phi squared, right? You add the warp factor in front of dx squared, which is some a squared of phi dx squared. And that is like, then you immediately broaden your scope of theories. And these theories we get from supersymmetric D-branes are all of this type. So I think you can say that this is maybe a penetration of the C=1 barrier. But on the other side, it's just going from, I think of this C=1 matrix model, it's just matrices are at a point, right? They cannot, it cannot disintegrate in a sense, right? Just very heuristically. But once you take a matrix in 1+1 dimension, then it can just fall apart into bits. So then you really should be gauging this series. So it's all part of this whole confining string story. So yeah, I would say that to penetrate to construct models that go above C=1, you really have to gauge the matrix model. And even the C=1 matrix model, we can always think of it as gauged. I think. In particular, this Zamolodchikov D0 brane picture always comes with a gauge field. So you do get a gauged model.
So Are there any other questions or comments?
I have a
Yes.
question or comment. Going back, sorry. Should I ask? Or?
Yeah, and then it's Berens, David.
Okay, yeah. Going back to what Dio was asking. So, if you from this latest development of Sachenko and Stanford, if you look at the matrix dual to the C smaller than 1 minimal string or whatever, that matrix seems to be the Hamiltonian that should be interpreted as a average over Hamiltonians. But in the C=1, the matrix is a degree of freedom that you put in a definite Hamiltonian. So that aspect does seem very different from C=1 that sees
right. Yeah,
smaller than 1.
I think that's one of the big questions, is how to connect these two. Yeah, the JT philosophy is more like the original Wigner philosophy, right? Where you take the limit of SYK model to low energies. And then, so maybe that's a good topic for more discussion.
So I will give one last question to David Berenstein, and then I think we should move forward because we have plenty of time in the discussion session to continue with more questions. So okay. One last question by David.
In my understanding, a lot of the connections with string theory and matrix models have to do with these matrix mechanics with an unbounded potential from below. Is there a similar story with the ones that have a bounded potential, where it's a string theory interpretation of just things that have not just a scattering to infinity, but just things with a discrete spectrum and a let's say positive specific heat or some.
Well, for example, the slide I'm showing now, you start from a bounded potential, right? Just a double well potential. Yeah, for this type 0b model, you start with a bounded potential like this, and then you just take a certain limit of it and you get this, but in the end, there is a bounded system behind it.
Maybe also the unitary matrix models.
Right. So maybe this boundedness versus unboundedness is, yeah, one could say that because of, if you start with this, say, double well system, it gives you some very definite non-perturbative definition of the theory. If you can solve this double well oscillator very precisely, you know the energy exactly. You can compute the number and then take some limit of it.
Yeah, but does it still have a string theory interpretation?
I hope so. I mean, we're out of paper. I mean, certainly to all others it does, and I think that's part of the reason why we were excited in 2003 that it looked perfectly non-perturbatively stable. I mean, now Baltazar, Yin, and Rodriguez are telling us that even the unbounded ones have some non-perturbative interpretation. But yeah, one thing that, and I think this will be talked about, is the precise non-perturbative story for this type 0b. But okay. You agree that it's bounded, right?
Well, yes, no, but the statement is that there's a certain sense in which how you bound it is not quite universal. And
yeah, that's the question there. You can add some wiggles here, and perturbatively it's still the same. But for any of these models, you don't have any issue with it being a formal problem. It makes sense at finite n, for example.
Right.
So this problem, you can either think of this D0 brains in type 0b theory, or you can even develop some kind of discretized expansion for it, right? Think about one of these minima, for example.
But I mean, Igor, I think David's question isn't about what you can do in the matrix model, but what that means in string theory, right? I mean, it's
yeah. What altering the details of the potential in string theory? Yeah, that I don't exactly know the answer. yeah, I mean, it could be that this story still has some free parameters in the non-perturbative. I mean, one possibility is that somehow when you go to the double scaling limit, these parameters disappear. But maybe she knows the answer. I know he's been working on this.
Okay, thank you.
I will come out in my talk, but I don't have a full answer. I mean, I don't have a real answer. But.
Okay.
Okay, I think we can keep our questions for later also to come back. And we should thank again Igor for the very nice talk and the very nice, and all of you for the very nice discussion.
Yeah, thank you very much. Thank you.
So now let's go to C, who will continue.
Okay, let me share my screen. Okay, so I will try to be a bit as brief as I can. So I'm gonna talk about just comment on some updates on the equals-1 string theory as well as the type 0 string theory in two-dimensional space-time, and also set the stage for some of the discussions that will happen in the next couple of days. I'm going to take the post-DOZZ perspective on the subject. So to me, Liouville theory would not be viewed as a deformation of linear Liouville. It's just a perfectly well-defined CFT on its own. There's a Liouville field phi, there's the Liouville potential, but the states of Liouville theory are labeled by the Liouville momentum P, which is a positive real number, and I'll just denote the vertex operated by VP. So the equals-1 string theory, as we all know, involves on the worksheet the free boson and equals 25 Liouville theory, and we believe that there's this matrix model dual that I'll elaborate on in a bit. So the basic statement of the duality is that the closure excitations are supposed to be due to collective excitations of the Fermi surface, at least in the perturbative sense. There's also a way to view these collective excitations as particle hole pairs, which are kind of important for certain computations. So it's not surprising that the Lorentz excitations of the Fermi surface can be thought of as exciting a fermion, putting it the other way around, hole and the particle. Okay, so the basic observables that one would be interested in, not the only observable, the basic observables would be closure scattering amplitude. Now I should say that we're talking about closure states that asymptotically behave like massless particles, maybe 1 + 1d. I mean, near the Liouville wall, there's some non-trivial interaction, but in the asymptotic region, they behave like massless particles. And massless scattering in 1 + 1 dimension is subtle. It's subtle because all the wave packets move at speed of light in the asymptotic region, and therefore you can't, they don't automatically separate. This is unlike the scattering of massless particles in more than 2 dimensions, or massive particle in 2 or higher dimensions, in which case generic wave packets will separate in the asymptotic path in the future. So there's a well-defined S matrix. You could question whether the S matrix should have been well-defined in the first place in these theories. But somehow they are, but there are important subtleties that come along with it, which I probably won't have the time to elaborate in the talk, but we can discuss later. So the matrix model is famously solved, at least perturbatively to all order, but also non-perturbatively. We'll come back to that. And here, I mean, Igor lists many references. Here, I'll just mention the approach, which will be convenient for the generalization I'll discuss later due to more Platon and Regulum. So basically, you represent these closed strings as particle hole pairs, and the particle and the hole, which are the particle is just the fermion, free fermion itself. The scattering is a non-relativistic scattering problem, and the hole has its own reflection amplitude that one can study based on what the Fermi C is to begin with. And so there's a systematic procedure, and a very straightforward procedure to compute arbitrary n to m scattering amplitudes of these collective excitations. So this is well known, but the important question, or the important check of the duality, is to to do this from the worldsheet perspective. And so so I'm going to take the post-DOZZ perspective. So before DOZZ, people did their tricks to try to compute this amplitude. Sometimes they're legal, sometimes they're not legal, and sometimes they gave the right answer, sometimes they didn't. We kind of understand why that is so in retrospect, but I'm just going to give the DOZZ perspective. So at the level of tree amplitude, so the 3 point is just easily computed by DOZZ correlator. It turns out that the DOZZ formula, which is which generally very complicated for the Liouville 3-point function, if you impose the Mass-Shaw condition for the 3-point amplitude, it collapses to some very simple expression, and it just agrees with the matrix model answer. And this historically notorious Lexel factor is automatically taken care of by if you normalize the Liouville vertex operator properly by normalizing 2-point function. So it's not an issue here, so I won't even discuss that. For the endpoint, say tree level amplitude, there was the old trick of annular continuation from the resonance momenta, and this, as I alluded to, was sometimes often works, but sometimes it gives the wrong answer, and we kind of understand why that is so, because there's some subtleties about poles and the DOZZ structure constant crossing the contour of Liouville momenta integration, things like that. So the honest computation of this beyond the 3 points, actually, as far as I know, wasn't done until relatively recently. And in fact, this is a kind of the accidental reason how I and Bruno Baldassar and Victor Rodriguez kind of got into the subject recently, because in some unrelated work, trying to do 2D conformal bootstrap with Scott Collier and Min-Jae Cho, we developed some recursion relations that allow us to efficiently calculate not just sphere, but a higher genus Virasoro conformal block. And we wanted to apply that to some problem. And one perfect application of that is to calculate Liouville correlator on not just a sphere, but on the torus, for example, or higher genus Riemann surfaces. We can do this efficiently and numerically. And so we did this for the 4 points, and it agreed in a miraculous way with the matrix model prediction, which is the formula looks like this. It depends on the energy of the incoming particle omega and outgoing particle omega 1, omega 2, omega 3, so let's say for the 1 to 3 scattering. The worldsheet computation is really quite complicated because you have to take the generic Virasoro conformal block, which is multiplied by the DOZZ structure constants, and integrating the Liouville momenta to get the Liouville 4-point function. This is a horribly complicated object. There's no simple expression. But if you integrate over the moduli of the 4-puncture sphere, and after taking care of the appropriate annular continuation or the regularization, you land numerically at this very beautiful answer. And I'm sure one can try to prove this more carefully by studying annular continuation of this object. But we just at the time wanted to test if this works, and it works beautifully. And then one can go on to calculate one loop amplitude of a one loop as matrix element. This is really something that I don't, as far as I know, cannot be done using this old resonance momentum trick. But we can just calculate directly the torus 2-point amplitude. First, in Liouville theory, you integrate over the conformal block of the torus 2 points, so these can be calculated numerically in an efficient way. But then you have to integrate over the 2 internal Liouville momenta to get the torus 2-point function. Depending on where you are in the modular space, one or the other conformal block channel might be more efficient. And then you integrate over the relative position of the 2 points, and then further you integrate over the modular space to torus. So this is a pretty complicated integral to do, and the only way we could do that is by numerically interpreting these functions over the space of integration. And I introduced some numerical error. At the end of the day, we end up with, after some hard work, end up with a 1% numerical agreement with this prediction of the matrix model. This is for the 1-to-1 scattering amplitude, where the energy of the ingoing and outgoing string is omega. So it's kind of a funny looking formula. I won't get into this into much detail right now, but I just mention that the real part of this is actually fixed by unitarity cut. It's related to the 1-to-2 amplitude. So this has to work. But if scattering is particularly unitary, but the imaginary part is a genuinely non-trivial prediction, and that agrees with the worldsheet computation. So perturbability seems to work beautifully, but I should say that actually the story is not complete. As is well known, the Fermi sea in the matrix model has the Fermi energy, which is minus mu. So this energy is here is 0. The Fermi surface minus mu. So this is in the h bar equals 1 convention, of course. So 1 over mu is the semi-classical expansion parameter for the fermion collective excitation. Now, the identification of that with a string perturbation theory is that the string coupling up to some factor 2 pi is supposed to be equal to 1 over mu. This is our expectation, but there's no proof of this as far as I know, because in particular, there could be corrections of 1 over mu squared plus da da da. Actually, so far, all of the computation, tree level, and this one loop one-to-one amplitude do not test whether there are corrections to this. Right? So that correction could be there. We don't actually know. The easiest computation that could potentially see this correction is the one loop 1 to 2 amplitude. This hasn't been done, by the way. So this is one of the, it will be a nice computation to do, but it will require some, I mean, in a stupid way to do it, which is the only way I know how to do it, will require some pretty tough numeric, but it can be done in principle. Okay, so now let me switch to the non-perturbative story. This was a story from last year. We think that this duality can be computed completely non-perturbatively, both on the matrix model side and on the worldsheet side. Now, the thing is, on the matrix model side, you might say that you can complete this any way you want, it's just some quantum mechanics, but there is a specific non-perturbative completion that just happens to land on the node that agrees with the d-syntron computation from the worldsheet perspective. So I'll be a bit brief about this, partially because I gave a bunch of talks on this recently, but also because it will be discussed in more detail tomorrow. The point is that, first of all, we're going to claim the closed string vacuum is not just filling the Fermi sea on the right side, because that's not quite well defined non-perturbatively, but we can declare to fill all the energy eigenstates that correspond to the scattering states of the fermion that look like this. They have some stuff coming from the right, scatter back out to the right, but then there's some tunneling amplitude to the left. So these are well-defined scattering states, demanding that there's no incoming flux from the left side. We fill all of these, and then we can talk about particle Hall excitation on top of this. The consequence of this prediction, of this prescription, is that while the particle reflection amplitude is always the same, it's given by this formula, is well known in this quantum mechanics of fermion, the Hall reflection amplitude effectively looks like the inverse of the particle reflection amplitude. So the Hall, which is not a real object, somehow has a reflection amplitude as much as slightly bigger than 1 non-perturbatively. But that appears to be what's happening. There's some interesting thing one can say about this detailed analytic structure of this, but I won't get into that for the moment. I'll just say, because this is kind of a very brief overview of the status, I'll just say that if you take this Hall reflection amplitude and plug into the formula of Moore, Spesser, and Rangulam that converts these reflection amplitudes to of the particle and holes into scattering amplitude of the collective excitation, then they perfectly agree up to some small ambiguities that I'll comment on later to the instant computation that's done from the worldsheet perspective. That is, you declare that we're going to take into account worldsheets that have boundaries. These boundaries end on the d-instanton. So these are open strings that end on d-instanton. You have to calculate this worldsheet amplitude with boundaries, and you have to integrate over the d-instanton moduli space, which is in this case very simple because these instantons are point-like in time, and so basically you just integrate over the position of several points in time with some suitable measure. So there's some effort going into determining what this measure is, but that story we think we have figured out. Victor Rodriguez will have something to say about that in more detail tomorrow. So this actually, in an amazing way, kind of works due to some miraculous combinatorics to all-instant order, which is order e to the minus n over gs. But that's not everything, because you also have some gs to the m, the minus n over gs, which involves diagrams of different topologies. So actually, the worksheet prescription that I kind of outlined here has some potential ambiguity. One ambiguity is just the overall normalization. So this, we don't know any way to fix other than by matching with the matrix model, but it's some overall normalization constant that can fix once for all. A more interesting issue is this cancellation of divergence, which is observed by Polchinski in this context back in 1994. That is, if you compute, this will be say for one instanton will be at order gs times e to the minus 1 over gs. At this order, you have, say, for one-to-one scattering, you have diagram like this, you have diagram like this. Each diagram actually has open string divergence of the open string collecting mode of the instanton that kind of propagates through this cut, but they cancel. So the cancellation was understood by Polchinski back in 1994, but the ambiguity has to do with the finite part after you cancel this divergence, which is of a logarithmic nature. So when we first tried to match this with the matrix model, we just try to match it with the matrix model by fixing it. To fix this ambiguity, we simply by matching this, by fitting a constant, by matching the results of the matrix model, which worked. But then Ashok-Sen explained how this can be, in principle, fixed in an unambiguous way by open plus closed string field theory. So some aspects of this will also be discussed by Min-Jae Cho tomorrow. There's some partial agreement between the string field theory results and the matching with the matrix model. But the gist here, maybe just to summarize the status of this, is that we believe that this duality between C+1 string theory from the worksheet and the matrix model is actually non-perturbatively complete in a suitable sense. But in order to take account of, in order to compute the instanton corrections systematically, string field theory is actually logically necessary. There's some ambiguity that would not have been possible to fix without using open plus closed string field theory on the instanton. And that's not specialized to just non-critical string theory. Oh, sorry. That would, this ambiguity would also arise in ordinary, say, type 2B superstring theory in Tandy if you go beyond the order that has been studied, considered previously in the literature, say, in the work of Green and Gasparov. So Min-Jae Cho will have something to say about this tomorrow, I think. So now let me, so far I talked about closed strings. Let me now come to the brain. So in the C+1 string theory, famously, there are the ZZ brains and the ZZ brains. So the ZZ brains, as already mentioned, has an interpretation of, in the matrix model side, as a fermion that's kind of brought to the top of the potential. In the linear theory, it's some stuff that's some kind of zero brain localized in a strong coupling region. Now, as I mentioned sort of after Igor's talk, one curious thing about this is that if you think about what the open string tachyon dynamics on ZZ brain is, it's expected that it's characterized by some kind of effective potential that the heuristic looks like, as a cartoon looks like what I'm plotting here. Okay, on one side it's unbounded, on the other side it's supposed to reach a finite energy local minimum, and that's supposed to represent the condensation of the tachyon in which the brain disappears. So this was famously conjectured by Sim and proven by Martin Schnabel. Now the conjecture by Sim and Martin Schnabel were originally formulated in the context of the C+26 critical string theory, but it's completely identical. I mean, the actual open string field theory solution for the ZZ brain is completely identical. So you can just borrow the same solution. So now this picture, looks kind of like the profile of the effective potential will be solved by the fermion if you include the top of the Fermi seed. Okay, so it'd be interesting to actually demonstrate that. And as far as I know, this has not been shown that this exactly agrees with the effective dynamics of fermion, in the presence of the Fermi seed. So that to me is still a outstanding open question here. I think if one can show that, then it will be much closer to a proof of the duality. But now let me come back to the physically richer question of concerning FDT brains, because the ZZ brain is a kind of unstable object. I mean, it has some significance, but let me discuss FDT brain. So this brain, as a boundary condition, Liebel theory is it looks like, you know, it's often said that this is like a Neumann type boundary condition. It's so here I'm drawing the picture of the Liebel direction, and the brain should be really thought of as a semi-infinite object that extends from some finite distance all the way to asymptotic infinity. So the brain is parameterized by a parameter which I call S. That's roughly speaking the distance between from the tip of the brain to the trunk coupling region. Now, of course, the trunk coupling region is a bit not completely well defined, but you can say that it's roughly where the ZZ brain is, quote unquote. So this can be all made very precise in the language of the CFD, of course. Now, on the brain, there lives the open string. So I depict this open string by this blue thing here. This is the open string, and it can propagate up and down the brain, and it can scatter with the closed string. For example, the open string can split, the closed string can split off, and they can interact. Now, the presence, I want to emphasize that the presence of FZZ brain changes asymptotics because it's in some sense space filling, at least in the asymptotic region. So you should think of this as a different background. If you add FZZ brain, it's a different background for the sequence string theory. And there's no reason to believe that it can be characterized by some state in the original matrix model. In fact, it's believed that we have to extend the matrix model if you want to describe the presence of FZZ brain. So there was a vague proposal put forth by David Giotto in 2005 that suggests that maybe the matrix model dual involves some fundamental matter. But the details of this proposal, I think this is morally correct, but the details has yet to be fleshed out. What is much better understood, though, is a specific limit of this setup, which is now known as the long string limit that was studied by Malacina in 2005. So this limit in which so I said this parameter S was the distance between the tip of the FZZ brain to the trunk coupling region. Now let's take the limit S to infinity. So in the limit S goes to infinity, FZZ brain retreats to the weak coupling region. So the influence of the brain is sort of gone, but you consider a very, very high energy open string that such that its high energy is high enough that, you know, when it comes in, it moves in, its ends are of course stuck on the brain, but the rest of the string can extend all the way into the bulk, all the way to some region where the string coupling is, which is exponentially small in the atomic region, but it becomes finite in this trunk in this middle here. Okay, so now, so the length of this thing is S. So the length of the open string is roughly speaking 2S plus some finite correction. So in the limit we're talking about, this long string limit, the energy of the open string omega goes to infinity. The S parameter for the FZZ brain also goes to infinity. But the difference between omega and 2S is going to be a fixed quantity that is going to be a finite quantity. So we usually refer to this as the renormalized energy of the long string. Right? So whenever I speak the long string limit, or the long string should be thought as obtained by this limit, where the renormalized energy epsilon is finite. It's a finite and meaningful quantity. What is not completely obvious, even though heuristically kind of makes sense, is that despite that these long strings have infinite actual energy, their dynamics is really governed by this finite renormalized energy, and they have actually completely well defined. In the long string limit, when we take this S goes to infinity limit, by keeping epsilon finite, they have perfectly well defined and finite scattering amplitudes with each other, as well as with closed strings. So this we demonstrated numerically very explicitly in a paper from a couple of years ago. And we studied two kind of amplitudes explicitly. One is the tree level long goes to long plus close. The other one is long plus long going to long plus long. So the scattering of a pair of long strings by kind of reconnecting. So, you know, these computations are completely straightforward in principle because we know all the structure constants thanks to Teschner of Liebel theory with FZZ boundary condition. But these formulas are horrendously complicated. So they are much more complicated than the DOZZ formula. And then you integrate against conformal blocks and you take this upper limit. So numerically, this is a bit challenging, but we did it. And the results matched with the matrix model computation beautifully. This matrix model computation is actually also very non-trivial. I think Bruno will discuss some, sketch this, a little bit of this in his talk on Wednesday. So I just want to say the words that is going to involve non-single, so-called non-single sector, in fact, adjoint and bi-adjoint sector and so forth. So for example, a single long string asymptotic state will be described by some wave function in the eigenvalues of fermions together with some indices in this adjoint representation. And already to identify the single long string asymptotic state, how it's representing the matrix model was already non-trivial. And this is a problem that was beautifully formulated by Juan in 2005 and subsequently solved by Tchaikovsky in a very beautiful paper. There's a very complicated expression for this long string wave function. And we use that to calculate the scattering amplitude of long string with the closed string in the matrix model, and it matches in a miraculous way with the worksheet computation. So, so that was the substantial evidence that this duality actually works beautifully, at least in the long string limit. Now, you know, this long string maybe it's kind of a curiosity, but to me, one of the big reasons to be interested in FDD brain is the connection to the black holes. So in Huang's paper from 2005, there's a tremendous amount of amazing content of the paper. And one of the things that was discussed in the paper, which for many years I never understood, was hiding in one section in the paper that in which he discusses the 12th limit of FDD brain. So what you do is the following. So you know, you consider this a stack of FDD brains. You can arrange them to be any way you want, but let's just for simplicity, let's say that they all have the same S parameter. Okay, so they come from infinity and they end up some distance that's S away from the strong coupling region, and you have a large number of them, NF of them. You want to take the limit where NF goes to infinity and S goes to infinity at the same time, so that on one hand, because the brain has retreated to the asymptotic region, their influence on the closed string becomes very small. The open string states kind of decouple in some sense, unless they have very high energy, but if they don't, then they kind of decouple. But as usual, you know, if the number of them is very large, then that can compensate for this diminishing effect as you push them off to infinity. And as a result, you might expect that the influence of this FDD brain on the closed string background remains. This turned out to be the case. And there's some preliminary evidence of this, and it's kind of partially spelled out in Juan's paper. Partially, this is some work in progress, and maybe Bruno will also sketch on this. But you can demonstrate, I think this is, as I said, still work in progress. That it appears that this non-trivial Twitter-like scaling limit is only non-trivial at finite temperature. So at zero temperature, it will end up being nothing. It will end up have no influence on closed string background. It will have a non-trivial consequence only if you have some temperature, which is 1 over 2 pi r, and r is less than some critical value, which is some alpha prime because 1 unit equal to 2. Okay, so it's above some temperature, some critical temperature. It turns out the influence will survive, and there's some effective coupling. So the quantity you want to hold fixed is NF times e to the minus beta s, basically. And then one can demonstrate from the worksheet perspective that I should say that this is, again, not completely rigorous, but I think it's more or less correct. That if you take the decoupling limit, the result of this is a closed string background deformation that's of this sine dual type. More precisely, the T dual of sine dual. So I wrote it in this way. So the sum dual, this VP is a analytic continuation of the dual vertex operator to imaginary dual momenta, stressed by this cosine of x left minus x right, which is the T dual of the sine dual coupling. So now this deformation is often thought to be in, you know, as you tune lambda from 0 to very large, it's going to allow you to interpolate between the T equals 1 vacuum and the 2D black hole. So I would say that the large lambda limit, the large Swift coupling limit, the Swift coupling, remember, was defined in this way. The large Swift coupling limit is going to lead to 2D black hole. And so far, this is just from the worksheet perspective. Now, from the matrix model, even though exactly what the FZT brains are due to is a little bit murky, but we think that we know about these long strings. And so the suggestion, a straightforward suggestion is that this should be due to, in the matrix model, a thermal bath of long strings. And now that sounds a little bit funny because the long string have infinite energy, but actually because of this funny scaling, because this exponentially large number of species of the long strings actually can compensate for this diminishing Boltzmann factor due to their infinite energy. So we think that actually the thermodynamics of long strings makes sense, and the thermal bath of long strings is supposed to be due to this Stein-Weber deformation, the T2 of Stein-Weber deformation. Anyway, that's a story that Bruno might sketch a bit more in his talk. So this is all I'm going to say about sequence one string theory. I'll make a few comments, very brief comments, about other type 0 2D string theories, which are formulated in NSR formalism. So the worksheet involves some boson X0 and fermion partner and N equals 1 Liouville now with a BC beta gamma system, just like NSR superstring. Now, depending on a different type of GSO projection, there's the so-called type 0B and type 0A. So the matter content of the CRC cohomology of the worksheet theory that represent asymptotic states of closed strings are a little different. So in type 2B, there are two kind of scalar that look like asymptotic, that looks like 1 + 1 dimensional massless particles, one from NS sector and one from R sector. In type 0A, there's only one kind of scalar, but there are D0 branes. In type 0B, there are no charged D0 branes. And as Igor already mentioned, the type 0B is supposed to be due to the matrix quantum mechanics of the same Hamiltonian, but you still have both sides of the potential. The type 0A, the picture, I like to think about it, at least the proposal is the following. So it's like you start with a two-dimensional, you start with a particle moving in two-dimensional inverted harmonic potential, but you're going to restrict all the fermions to a fixed angular momentum sector, individual fermions. Anyway, this is just to motivate that the result of that, and the angular momentum has to do with the D0 brane charge. So if you have no D0 brane in the background, you just restrict all the fermions to zero angular momentum sector. And the results in a effective potential that looks like this, there's some hard wall, and the Fermi C is on the right. And on the left, there's this, you can either go up or go down depending on the D0 brane charge, like so. Okay, so that's a lot of dualities actually, and you can ask what are the evidence for this apart from this kind of heuristic argument. And to me, there has not been that much check of this. I don't have any reason to doubt that they are correct. In fact, they are kind of miraculous to me. But the checks are fairly limited. For example, you see the right half of, so I should first emphasize the worksheet theory is totally different from sequence one string theory. You have to integrate over, either super Riemann surfaces or you're working in NSR formalism, you can use significant operator and things like that. It's totally different worksheet theory. And yet, sort of the right half of your B of the excitations over here, perturbatively, it's supposed to be identical to sequence one string theory. So these correspond to some combination of NS, NS, and R degrees of freedom. So that already is kind of mysterious to me. I'm not aware of proof of this from the worksheet, even though we believe it's correct. And it's actually also supposed to agree with the 0A at tree level, essentially because there's a difference in the GSO projection. This is something you can motivate from the worksheet. Now that's actually not obvious from the matrix model because the matrix model of 0A looks totally different. But actually, if you plug into the known formula from the matrix model and check, actually they do agree between 0B and 0A, the right half of the 0B, they do agree with 0A at tree level, but actually they're different than 1 loop. Okay, so they're explicitly different. So it'll be interesting to check all of this on the worksheet. As far as I know, this has never been done. Non-perturbatively, well, of course, this is kind of very natural. Using the non-perturbatively, this is perfectly well defined. Now, the difference between this and the sequence one story is that in the sequence one story, the D instanton is supposed to be bounces. So I guess I didn't say this, but it's very natural that it's supposed to be a bounce solution. In type 0B, the D instantons are charged. So this should represent tunneling from right to left and from left to right. So now, okay, there are different processes you can imagine. So for example, you can have a closing on the right, which is represented by particle-Hole pair. The particle can reflect, the Hole also reflects. So this can be thought of as a closing one-to-one amplitude in type 0b of a particular closing state that's some combination of NS, NS, and R states. But you can also have a different process in which a closed string tunnels to the left over here, where the Hole reflects. So this is kind of a funny process because if you do this, you end up with a different total fermion number on the left versus on the right. Even though this there are infinite number of fermions, so this looks like excitation of some vacuum, just like the original vacuum, but technically they're distinct. It's a distinct state, distinct vacuum state, because the fermion number differs by 1 on the left, at least perturbably speaking. So it's believed that this is supposed to represent transition between different vacua of the type 0b string theory. And this can only occur non-perturbatively, right? So so far we have done some preliminary study of this kind of amplitude in the type 0b context by comparing the exact matrix model results, from which you can extract the non-perturbative piece that has to do with the bounds to a worldsheet computation. Now this is a little different from C=1 now, both from the matrix model and from the worldsheet. From the matrix model, the difference is that the Hole is a different Hole. It's a Hole in a different Fermi seed. So the reflection amplitude of the Hole is slightly different. But from the worldsheet point of view, it's a different theory on the worldsheet. Moreover, what would be the analogous to one incident amplitude in C=1 is actually due to a pair of D instanton and anti-D instanton. But so far to the extent we have checked with some appropriate contour prescription over in the integration of instant MOSFET, it seems to work. So there's some work in progress. Okay, so I'm pretty much finished. I'm gonna end with a few questions. I mean, there are many more general questions one can ask, but I'm just gonna pose a few immediate questions, some of which are similar to what Igor has already posed. You know, you can imagine modifying, of course, the matrix model in various ways. I claim that, you know, the string theory prefers the matrix model to not be modified, actually, to be this harmonic, inverted harmonic potential. But you can ask, what if you deform the potential? What string theory is this due to? Well, the thing is, from the worldsheet perspective, well, okay. So, you know, if you only modify this potential somewhere in here, the perturbation theory is exactly the same as before, but non-perturbatively they're different. So, you know, if we claim to get a D-instanton correction to match with the old original matrix model, well, what if you do this? Is this due to some string theory or not? Now, I don't have an answer to this, but I think it'll be interesting to discuss. Another thing is what also Igor mentioned and David earlier was asking, what about, you know, when we actually, you know, say, quote unquote, complete, or maybe that's not the right word to use, deform the matrix model to make the potential actually bounded. Okay, so what is this thing due to? A very naive guess is that you might say that, okay, well, it looks static, so, you know, maybe it's you just deform the worldsheet CFT. But it cannot be the free boson together with some compact C=25 CFT. There's just no way, because the compact C=25 CFT always contains the identity operator, and once you adjust with E to IKX, you give rise to tachyon. Okay, so that's not possible. Okay, but actually, this kind of deformation is more like we expect maybe can be obtained from the C=1 by worldsheet theory by deforming by operators like, you know, partial X naught to the some Carroll ring states from the free boson, not Carroll ring, ground ring states from the free boson, dressed by some and the continued trivial vertex operator of this type. But we don't, so, you know, these are kind of non-normalizable vertex operators you can write down. We don't know too much about, I don't know too much about what's the endpoint of, you know, if you deform the worldsheet CFT by these operators, and whether there's some useful way to characterize the resulting deformed worldsheet theory. so to me, this is largely still an unresolved issue from the worldsheet perspective, and it would be quite interesting to understand what's really going on. This is kind of tied to also the issue of non-critical strings more generally. I've been wondering a lot recently whether, a local CFT, equals 26, coupled to BC system is really necessary for the perturbative string. And I really don't see any reason why this has to be always the way to formulate a perturbative string theory. For one thing, even the NSR formalism of superstring is not really of this type, even though it's often said that the superstring, it's just the generalization of a bosonic string. You make the worldsheet theory supersymmetric, but it's really qualitatively quite different. Because for one thing, if you take the superstring worldsheet theory and separate out the BC system and group the rest into a equals 26 CFT, well, it does have central 26. You have the equals 15 superconformal matter theory of the NSR string together with the beta gamma system. But then you have to play the game with the picture changing and all that. And it's well known that beta gamma system have the spurious singularities correlators that can blow up at separate points. It's really not what one would call local CFT. That's not a CFT axiom. So the NSR string is really already not of this type, and maybe there's a way to reformulate through a different worldsheet theory with different BRC charge and so forth. But in general, I wonder whether this framework of CFT coupled to ghost is too restrictive to describe things like the QCD string, which are perfectly sensible relativistic string theories. So I will stop here. Thank you.
Okay, let's all thank C for this very nice talk and giving also all these subtleties. And are there any questions, comments?
By the way, I have one organizational question. Are we supposed to have a break before the next session?
Yes, we're supposed to have a break, and we start at in half an hour, I suppose. So we will have a break. But if there is some quick question now, we could have one or two questions only.
So I had a question about the comment about midway through both a comment and a question. So when you were discussing, the meaning of FZZT brains,
Yeah.
So if we ask the analogous question for the C less than 1 models, it's completely clear. Well, actually, for C equals 1, it's also relatively clear that on the worldsheet, these are just brains which are Legendre transforms of macroscopic loops. So in the old days, the sort of like first incarnation that Igor was describing in the early 90s, people thought a lot about how you put in a worldsheet boundary with fixed proper length. And so that's inserting an operator, there are various ways of describing it, but basically it's an open string boundary condition with, roughly speaking, boundary Liouville theory and a Neumann boundary condition. And the boundary Liouville cosmological constant is the Legendre transform of the boundary length and is related to your parameter S.
Right.
So, and furthermore, I want to say that this Tuft limit, I think, was analyzed. Volodia probably has more to say, but I think he was one of the first people to study that phase diagram where you include some gas of loops in the matrix model and study the phase diagram. So I think there is some understanding of what these things are, at least from the worldsheet point of view.
Oh, I mean, from the worksheet, of course, we know these boundary conditions completely, right? I mean, we can solve. I mean, Sechner has solved this completely. That's why we're able to calculate these long string amplitudes, because we actually start with open string on the SDD brane and then explicitly take the long string limit. But the question, I think, at some point I was posing.
Right.
Well,
so.
Posing, but what's about the matrix model description? So,
right. So it is precisely. So you insert such indeed you insert such a macroscopic loop by one way of describing it is to add a fundamental.
Fundamental fermion. That was David's proposal. I mean, I'm not saying the proposal is necessarily wrong, but to me it has not been made precise because, for example, I don't know how to identify the parameters of the matrix model with S or even to see the open string degrees of freedom. I think so. You're basically saying that when you integrate out this fermion, they basically produce some determinant operator where you insert as this loop operator.
Exactly. Exactly.
I think that should be roughly correct. It's just that to me it seems that there's a lot of freedom you can play with on the matrix model side because the fermions, fundamental fermions, can have coupling to the matrix degree of freedom. Are they cubic coupling or they're not? I don't know how to determine that without a more detailed just matching of observables, or I also don't know an argument that can say precisely what the coupling of the fermion is. That's my complaint about this.
By the way, my paper was about C equals 0 open and closed strings, but there was after that the paper of Bulatov also in the old times, where he considered precisely the matrix quantum mechanics with this gas of open boundaries of open strings. So it may be good to look at it because it's not so simple to include boundaries which also live in this one-dimensional space, which fluctuate in one-dimensional space.
Okay, can I ask a quick question? So you basically have, if I understood correctly, some approach to pure long string amplitudes or pure winding modes, right? Add this.
Sorry, wait. These
like
are,
if you have four long string amplitudes.
No. I mean, the long string has nothing to do with the winding modes, right? So my point of view here is that the long string is nothing but this high energy limit of a open string on FTD brane. So these are ordinary open closed amplitude, that tree level I'm talking about here. There's no winding mode. And I'm not, this computation by itself is zero. This is zero. There's no final temperature here. Later I was mentioning something different. So later I was talking about the final temperature, but I didn't show you any calculation from the worksheet. So indeed, the final temperature, one has to, if you want to compare observables such as S matrix, you have to try to make sense of this final temperature S matrix, which I think it does make sense in this context. The observables that I know should be well defined, should be at the final temperature. So you have a compact boson on the worksheet. You are allowed to have this winding insertion, but the actual asymptotic states are still non-winding states. They are, states with ordinary momentum. Now it's actually tricky to compute this. I mean, in fact, we almost never do this in string theory, string perturbation theory, which is, you might want to say that you started with the closed string mode, so either with winding or with momentum, but the momentum has to be imaginary momentum or imaginary energy that takes this Matsubara frequency, right? And then you can continue to real energy, and you're hoping that the result makes sense. Luckily, we know how to do this computation, at least without this deformation, in the matrix model. In fact, you have computed this. You have this in your right?
That's what I wanted to bring up, that I think we did the computation for pure momentum modes in the compact case. Then we can T-dualize it and get pure winding modes, right?
That's right. In fact, precisely because the T-dual relation, we're currently investigating the contribution to the correction to the black hole free energy by using these amplitudes momentum as everything equals to winding. But for the mixed ones, I don't know any trick to calculate it.
But for example, even the unmixed ones, have people really reproduced using non-singlet states, the say pure winding ones, and show
even before you talk about the non-singlet, even in the singlet sector, just equals to a vacuum finite temperature and to talk about the say the tree level scattering of you know some close strings at finite temperature. This is not a computation that has ever been done as far as I know from the world sheet. So of course, if you yeah, this is something that that we have a technology to do actually, because because the matrix model prediction is already known, and you can continue this to this Matsubara frequencies. And on the worldsheet, it's straightforward to calculate, at least numerically, the amplitude with this Matsubara frequency, to be careful with regularization. This numerics, at some point we were thinking about this, but we have not actually gotten the results. So I have no reason to doubt that it will work, but it has not, as far as I know, been checked from the worldsheet. And the non-singlet sector, in this context, on the worldsheet perspective, will require inserting this winding mode, and that certainly has not been done from directly.
Okay.
Okay, so since we don't have a lot of time left, and I'm sure that we will come back to these questions also after the talks of Bruno and other people, I think we should thank C again for this very nice talk, and all of you. And then we can reconvene in 20 minutes. We can have a small break if you want, or we can leave also open. I don't know. Sota has the.
Well, yeah. Well, you can keep being here, but you can also like first leave and then do something else and come back.
Yeah, we can go for 20 minutes, let's say, or so, and come back.
So
yeah.
I was just wondering whether it might be useful to look at the C equals 0 story, where this has already been all mapped out from the matrix model side, or whether that's too trivial for you.
Well, you know, actually, yeah. So for the most part, I've not been thinking about the C<1 story, just because there was no time, and I felt like it's not a priori obvious how the observables are defined. Of course, I mean, there has been many success in matching observables in C>1, but it's like, you know, you have to first guess the dictionary and then get it to work. So to me, one of the attractive features about the C=1 story is that you know, there's no ambiguity to. I mean, you know, this S matrix